In our Chapter 8 worksheet, the first question is, how many chiral carbons do the following monosaccharides have? So if you'll remember, chiral carbons have 4 different things attached to them. So you can't have, for example, at the bottom of this one here, it has 2 hydrogen and OH and then a carbon attached to it. So that would not be a chiral carbon. But all these in the middle would be considered a chiral carbon. So 1, 2, 3, 4. So all of those have 4 different things attached to the carbon. But the one on the end here and the one up here, those would not be considered chiral. So for this one, we have 4 chiral carbons. On this one, again, it's going to be the ones in the middle. So we have 1, 2, 3 chiral carbons. And then on here, so we have 2 at the top. So this one and this one would not be chiral. This one would not be chiral. But the ones between that, 1, 2, 3, would be considered chiral. Because again, you need 4 different things attached to the carbon. Okay, on this one, same thing. So the top 2 carbons would not be chiral. The bottom one is not, but the 2 in the middle would be considered chiral. Okay. And then the last one, we have this carbon and this carbon. So the top and the bottom are not chiral, but the ones in the middle, 1, 2, and 3, are chiral. Okay, so then the next question says, classify as an aldose or a ketose. So the first one has it written CHO, but really what that looks like is C, the double bond O, and then H. So anywhere it says CHO, that would be an aldose. So we're going to put an A here for aldose. This one is also an aldose, but this one is going to be a ketose because we have that carbonyl carbon right there on the second carbon. So remember, the aldose is going to have the aldehyde on the first carbon. The ketose will be on the second carbon. So this one's ketose. Same thing here. Okay, this one is ketose. And then we have the CHO up here, so this one is aldose. C says label each according to its number of carbon atoms. So you're just going to count the carbons in the chain. So for this first one, we have 1, 2, 3, 4, 5, 6. So 6 carbons, so it'd be hexose. I don't really have any room to write that, but hexose for the first one. And then the second one, we have 1, 2, 3, 4, 5. So that would be pentose. Okay. And then the third one, we have 1, 2, 3, 4, 5, 6. So that's also hexose because there's 6. And then this one would be 1, 2, 3, 4, 5, pentose. And then the last one, we have 1, 2, 3, 4, 5, also pentose. Okay, the last one is identify each Fisher projection as D sugar or L sugar. So on these, you'll have to remember that the OH on the last chiral carbon is what determines if we have a D sugar or an L sugar. So if it's to the right, it's going to be D. If it's to the left, it's going to be L. Just try and clear this off a little bit here. Okay, so the last chiral carbon, so this one right here, so that would be D because it's to the right. This one also D, D, and then you have to be careful here because it doesn't list it as ch2OH, so it's this one right here would also be D. So all of these represent a D sugar. Okay, and then we need to, on number 2, draw the enantiomer of the following monosaccharide. So remember, it's just the mirror image. So we're going to redraw this here, and we're going to put the OHs on the other side. 1, 2, 3. Okay, so we have our CH2OH at the bottom. And since all the OHs are on the right side for the picture they've given, we're going to put the OHs on the left side here. So this would be an L sugar that we're drawing right now. And then in the picture, that would be a D sugar, because again, it's about that last carbon. I'm going to redraw this. I'm just trying to squeeze it in there just to make sure. So again, we were just drawing the mirror image, so I'd put the OHs on the left side instead of the right side. That looks a little better. Okay. Number 3 says convert the above Fisher projection to a Hayworth structure. So we had, so I'm going to draw it sideways, and then we'll put it into the Hayworth. So if you had the OHs on the right, then you draw them going down. So I'm going to just turn this 90 degrees and then draw it with the OHs going down. Remember, this last OH that's in the chiral carbon is going to be the O that's in the ring. Okay, so we're going to go from that, and we only have 1, 2, 3, 4, 5 carbons. So we're going to draw this structure here, because this is the oxygen that's actually in the ring. Okay, so I'm just going to label the carbons. We have carbon 1, 2, 3, 4, and then carbon 5 actually comes up here, CH2OH. So just to match that with what we have over here, carbon 1, 2, 3, 4, and then 5. So then we need to put in our OHs. So again, if they're pointing down in our Fisher projection or to the right, we're going to point them down in the Hayworth structure. And then on this one, because remember this oxygen turns into an OH. Really, it just depends on whether you have an alpha or a beta configuration, so it doesn't matter. We'll just say we're going to have an alpha. So if it's alpha, it comes down. Okay, so that's on carbon 1, and then on carbon 2 we have the OH coming down. Carbon 3 also has the OH coming down, and then the one on carbon 4 is actually right here. Okay, that's that one in the ring, and then we have the CH2OH going up there. And that's it. So this would be the alpha, right? Anomer. If we wanted to draw the beta, then we would have drawn this OH going up instead of down. Okay, then we have convert the Hayworth structure to a Fisher projection. And we need to know whether to have a D or an L sugar. So we're just going to assume that this is going to be a D sugar. So just looking at how many carbons we have, this would be carbon 1. Oh, I'm sorry. This would be carbon 1, 2, 3, 4, 5, and 6. So we have 6 carbons in our structure. I'm going to draw it over here. Actually, 1, 2, 3, 4, 5, and 6 in that monosaccharide. So because we have this ch2OH right here, that's kind of an indicator that I have a ketone. So my second carbon is going to have the double bond O on it. And then the ch2OH is going to be above it. And then at the bottom, we're going to have ch2OH as well. And in the middle, we just need to figure out which way the OHs are going. So we have carbon 2, now carbon 3. The OH is going up, so we're going to draw it to the left. For carbon 4, the OH is coming down, so we're going to draw it to the right. And then on carbon 5, carbon 5 oxygen is right here, so we have to know if it's a D or an L sugar. And so we're just going to assume it's a D sugar, and we'll draw it to the right. And then on the other sides, it's the H's. So it would look like that. And then number 5 says draw the mutarotation of D-talose. So I'm actually going to come over here because I need a little more room. So I'm just going to draw D-talose for you. It has, it's an aldose. So, whoops. Let's try that again. Okay, so it's an aldose. So I'm just going to draw what it looks like real quick. And we have 1, 2, 3, 4, 5, 6 carbons. Okay, so 1, 2, 3, 4, 5, 6. Okay, and we have 3 OHs on the left. And then 1 on the right. Okay, so the first thing we're going to do is draw the Hayworth projection. So we'll start with the alpha anomer. So we have the oxygen. And then since it's alpha, we're going to draw the OH coming down. And then we have our CH2OH right here. So that's this one. That's what this one is. So just label these carbons real quick. We have carbon 1, 2, 3, 4, 5, and 6. Same thing over here. 1, 2, 3, 4, 5, and 6. So you can see how everything kind of lines up. So again, I've drawn the alpha anomer. So now we can put in our OHs. So we have carbon 1, now carbon 2. So it's to the left, so it's going to go up. Carbon 3, same thing, is going to go up. Carbon 4 also goes up. And then carbon 5, OH, is this O right here. So that's the alpha anomer. So then the mutarotation, what happens is we go from that to the open chain form. So I'm just going to draw the open chain form, but on its side here. So we would have the OH here, and then the 3 OH on this side. Okay, and then it goes to the beta anomer. So we're going to redraw that. So here we need the beta to go up, and then all the other OHs are the same. Maybe that O doesn't look real great. Okay. Okay, so that would be the beta. So alpha on the top, and then it opens up to the chain, and then goes back into the beta anomer. It says, for the following Hayworth structure, number all the carbon atoms and identify the anomeric carbon as alpha or beta. So we'll number these. So this is going to be carbon 1, 2, 3, 4, 5, and 6. And then since the OH is going down here, it's going to be alpha. And then number 7 says, when monosaccharides are oxidized, what does it form? It forms a carboxylic acid. So just like aldehydes can be oxidized to form carboxylic acids. Normally you see it as a carboxylate ion. So either one. Okay, 8 says, draw the Fisher projection for the oxidation and reduction products for D-mannose. So for this one to be oxidized, it's going to form the carboxylate ion. So then everything else stays the same. Okay, so we have 2 OHs and then 2 OHs over here. So the only difference was what happened at the top where the aldehyde is. It now forms the carboxylate ion. Okay, I'm going to come back over here and draw what happens in the reduction process. So hydrogen is added to the top. So you're going to get CH2OH. So hydrogen's added to carbon as well as oxygen. So we get CH2OH. And then again, the middle part stays the same, the bottom part stays the same. Just changes what happens at the very top where the aldehyde is. So this is what it looks like for the reduction. And then number 9 says, draw the disaccharide that's formed when beta-D-galactose forms a glycidic bond with alpha-D-glucose. Okay, so we're going to draw that here. So we're going to do beta-D galactose first. Okay, so there's beta-D-galactose. So put a beta, so that means that oxygen's going up. And then alpha-D-glucose. So it's going to link up here on the fourth carbon. So since glucose is alpha, we want to draw the OH going down. So we're going to put it down here. And then finish drawing out glucose. And that's it. So again, galactose is beta, glucose here is alpha. Okay, draw the structure of the alpha and beta anomers and result from the reaction of methanol and ribose. So I'm going to do that one over here as well. So just to show you ribose, looks like this. Okay, so we're going to react that with methanol. Okay, so it's going to react right here. So we're going to get the OCH3 right here for the alpha anomer, OH coming down here. So all this stays the same. Whoa. Doesn't want to let me do that. Let's try this. And then CH2OH up here. So that would be the alpha. So the beta is just going to have it going up instead of coming down for the glycosidic bond. So it'll be OCH3 up here, and then OH, so it stays the same, CH2OH right there. So that would be the alpha and the beta anomers when methanol and ribose react. Okay, last thing. We're going to identify the disaccharide that fits each of the following descriptions. So first of all, not a reducing sugar would be sucrose. So A is sucrose. B, composed of 2 glucose units, would be maltose. C, milk sugar is lactose. D, hydrolysis gives glucose and fructose, would be sucrose. And then E, ordinary table sugar is also sucrose. F would be lactose, which is found in milk and milk products. G is malt sugar is maltose. And then last one, H, hydrolysis gives galactose, and glucose is going to be lactose. So those are the just different things that describe the disaccharides that we talked about. Now the polysaccharides, we're going to do the same thing. So A, for number 12, not digestible by humans, is cellulose. B, the storage form of carbohydrates in plants. There's 2, that's amylose and amylopectin. And then C contains only alpha 1,4 glycosidic bonds. That's going to be amylose. And then D, the most highly branched polysaccharide, that's glycogen. E, storage form of carbohydrates in animals, also glycogen. F contains only beta 1,4 glycosidic bonds, that's cellulose. And then G contains both alpha 1,4 glycosidic bonds and alpha 1,6 glycosidic bonds. That's going to be amylopectin and glycogen. Oops. So remember, they both had the same thing, except that amylopectin, the 1,6 link comes every 25 glucose units, and then for glycogen, it comes every 10 to 15 glucose units. And then H produces maltose during digestion. Is going to be amylose and then amylopectin as well.